In this lecture, we'll talk about dimensionality reduction. And in particular, we'll talk about two famous algorithms, SVD, which is a deterministic algorithm, and CUR, which is a probabilistic algorithm. So what is dimensionality reduction? Let's say that on the left, we have a bunch of data points in a two-dimensional space, and we can see that these points are actually, they do not lie randomly on a two-dimensional space. Instead, they lie very close to the red line, the straight line here. Therefore, although these are two-dimensional points, they actually can be represented using only one dimension, right? And similarly, if we look at the data points on the right, although these are three-dimensional data points, if you look into them carefully, you can see that they actually lie on a two-dimensional subspace. That means we can actually use two coordinates to represent three coordinates of the raw data points. So basically, the axes of this new subspace are effective representation of the data. For example, in this example on the right, the new axis is the new x here and new y here. As another example, let's say that we have a 7x5 matrix where each row actually represents how many products a customer purchased on each day. For example, this customer ABC Inc. purchased one product on Wednesday, one product on Thursday, and one product on Friday. And you might have noticed that actually the first four customers, they only purchase these products during the weekdays, while the last three customers, they only purchase product at the weekends. So basically, although this matrix has 5 columns, it's really a two-dimensional matrix because all the rows can be reconstructed by simply scaling 1, 1, 1, 0 here, or 0, 0, 0, 1, 1. In particular, the first row can, if we use this two basis vector to represent the 5-dimensional vector, then the first row can be simply represented using the length 2 vector of 1 and 0. And similarly, the second row can be represented by 0, can be represented by 2, 0. And the third one, of course, 1, 0. The fourth one would be 5, 0, etc., etc. And we can do this because the rank of this matrix is exactly 2. Therefore, we can use a two-dimensional basis to represent this large matrix. So what is the rank of a matrix? The rank of a matrix is the number of linearly independent rows of A. More concretely, let's say that we have this 3x3 matrix and it has a rank of 2. Why? This is because the first two rows are actually linearly independent. You can see that you cannot represent the first row by any linear operation of the second row and vice versa. So the rank of this matrix is at least 2. But all 3 rows are actually linearly dependent because the first row is actually equal to the sum of the second and the third row. You can see that if you add up the third row and the second row, you get exactly the first row. So the rank must be less than 3. Therefore, we have that the rank of this matrix is actually 2. So again, why do we care about low rank? Because if the matrix is low rank, then we can effectively reduce the dimensionality of the matrix without losing information. And basically the rank here is the final dimensionality that we can get. Like going back to the example of 3x3 matrix, let's say that we have row A, row B, and row C. And if we use the old basis vectors, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are basically the original XYZ axis. If we use these basis vectors, we have no choice but to represent these 3 data points using 3 coordinates. But if we use the new basis vectors, which is 1, 2, 1, -2, -3, and 1, we can actually represent these 3 rows using much shorter vectors. For example, the row A can be represented using 1, 0, and row B can be represented using 0, 1, and row C can be represented using 1, 1. So basically, by doing this, we have already reduced the number of coordinates from 3 to 2. And intuitively, the goal of dimensionality reduction is to discover the axis of data. For example, on the left here, rather than representing every point with 2 coordinates, we can instead represent each point with only 1 coordinate, and that coordinate corresponds to the position of the point on this red line. And by doing this, of course, we can incur a bit of error because the points do not exactly lie on the line. So basically, the best axis would be the axis that will incur the smallest amount of error. So why do we want to reduce dimensions? One possible reason is that we want to discover hidden correlations or topics from a larger matrix. For example, we might want to discover the words that occur commonly together. Let's say that we have 3 documents here, 1, 2, 3, represented by each row, and we have a vocabulary of only 4 words. So this is word 1, word 2, word 3, and word 4. And in the first document, it has only 2 words, which is word 1 and word 2. And the third document has 2 words, word 3 and word 4. And by performing dimensionality reduction, we can naturally find that word 1 and word 2 usually occur commonly together, and so do word 3 and word 4. Therefore, we can say that the first 2 words actually they belong to the same topics, and the last 2 words they belong to another topic. And the second reason that we want to reduce dimensions is that we may want to remove redundant or noisy features because not all words are useful. And the third one, naturally, is for interpretation and visualization. Imagine you have a large matrix and where each data point is like very high dimension, like 100 dimension for each data point. And there's no way you can look at the data. But if we can reduce the dimension from 100 to 2 or 3, then you can readily plot these data on the screen to visualize them, and you can discover some patterns from these plots. And the last reason is, of course, if we can perform dimensionality reduction effectively, we are compressing the data. And by compressing the data, we can get easier storage and processing of the data.